Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a new topic regarding the characteristics curves of hydraulic turbines. So, in this topic, we'll discuss about the performance and behavior of hydraulic turbines. That performance and behavior will be identified from the characteristics curves. So, the characteristics curves of a hydraulic turbine, okay, which will shows the exact behavior and performance of the turbine at different working conditions. And these curves actually identified by conducting of number of experiments, we can say, or number of tests, and the tests which are conducted at a different working conditions. So the characteristics curves actually of the hydraulic turbines can be identified by considering some different parameters. Some parameters are there. By this parameter we can able to draw, or we can draw the characteristics curves of hydraulic turbines. So what are the parameters are there in this? So the parameters actually what are considered, the first one is the basic things like what is the speed of the turbine. So first one is the speed of turbine, which is denoted by N, we can say. Second is head of the turbine. Second is head of the turbine, which is denoted by H. And the third one is very simple, that is discharge. What is the discharge from the turbine is coming out from the turbine. And the next one is fourth one. The fourth one is power. What is the power developed in the turbine, suppose. The fifth one is nothing but efficiency. In the efficiency, we need to consider the overall efficiency. So efficiency of the turbine. And the sixth one is the gate opening. The gate opening, or we can say the valve opening of the turbine. So these are the 6 parameters which are considered, or which are taken into consideration while performing the characteristics curves. And in these 6 parameters, what we are seeing here, out of these 6 parameters, actually 3 parameters are independent parameters. 3 parameters are taken which are independent parameters. These 3 parameters are nothing but, these are very simple, like these fast things. You can see that speed of the turbine, that is N, and next one is the H, and the last one is the Q. So these 3 parameters are nothing but called as independent parameters. Okay, these are called independent parameters. And here if you see, remaining are dependent, can be called, because power that will be calculated by considering these parameters. And anyway, so in these 3 parameters we need to consider a single parameter. Either you can consider the head. Suppose if you consider the head, then we need to keep one parameter, that is H equal to constant. Now one parameter gone means, like out of this total 6, or if you see how many are there here, total 3 are there. In this 3, one is taken out. Okay, and what are the other parameters are there, that will be performed along with this H. That means H remaining constant, and remaining parameters will be like taken into consideration, and that will be performed in various conditions. And these curves which are performed by conducting number of experiments, okay, that curves are called actually characteristics curves. Characteristics curves of the turbines. And these characteristic curves are actually, it is categorized into three types. First one is actually, that is called main characteristics curve. The first one is main characteristics curves, or that is nothing but we can call as, this is constant head curves. Okay, this is constant head curve. Similarly, the second one is nothing but operating characteristics curve. The second one is operating characteristics curve, or we used to call, that is here if I write, or this is constant constant head. This is constant head curve, and in this actually we need to consider the constant speed. The second one is operating characteristic curve. In this we need to consider constant speed, and the third one is nothing but that is Michel's curve. Okay, that is called Michel's curve. That is Michel's curve, or also you can say this is, see, H gone, N gone, and one more is there, that is nothing but our efficiency, not discharge. Discharge will be the one of the parameter in this curves. So here actually in the Michel's curve, that is we need to consider the constant efficiency in this point. So H and N taken. Okay, sometimes we used to think about the Q also in this point, but don't consider that one. Q will be in the parameter in this H and N. So out of these three, we'll discuss one by one. So in this lecture, we'll try to understand in this main characteristics curves or the constant head curves, how it is performing. Okay. So in the main characteristics curves, actually, as I told you, that we need to consider the constant head. We need to consider the constant head. By considering the constant head, we need to see how the performance are done. Like if I show you the diagram for this, if you see that for both the diagrams what you are seeing here, these are the diagrams are taken for different conditions or different turbines. So this one actually taken for the Pelton turbine. This is taken for the Pelton turbine, and these two diagrams are actually for the reaction turbine. In the reaction turbine, we know that two turbines basically we used to use. One is Francis one, another one is Francis, another one is Kaplan one. So in the Francis, we'll get, so okay, so this is Kaplan turbine and this is our Francis turbine. Okay, so we'll discuss about this, but here what I mean to say, that head is constant for both the turbines, and by keeping this head constant, we have performed among the unit speed and unit discharge. So this is kept as constant, head constant. So by keeping the head constant, we are going to perform between the unit speed versus unit discharge. This is the performance we are going to do. We will discuss about this one. So for what we will discuss, or for which turbine we will discuss? For we will discuss about the impulse turbine. We will discuss this for the impulse turbine, and another one is reaction turbine, because we know that the turbines are categorized into based on the different categories are there. So impulse and reactions are categorized based on the energy. Okay, so we'll discuss about this impulse turbine. So in the impulse turbine, we know that first one example of this is like a Pelton turbine or Pelton wheel turbine, and in the reaction turbine we have seen that two types are there. One is Francis, another one is Kaplan. Francis, another one is Kaplan. Even in that also propeller turbine is there and some other turbines are there, basic. So normally we used to use these are the turbines most regularly. Okay, and other parts like in this main characteristics curves, by keeping this one, as I told you, by keeping the head constant, first we'll discuss about the unit speed and unit discharge. Then we'll discuss about the like with respect to unit speed. With respect to unit speed, we'll compare this unit speed versus unit power. We'll discuss about the unit power. Similarly, unit speed versus efficiency. Okay, overall efficiency what we are going to discuss. So these things we'll discuss one by one. So I'll show you the diagram what I have taken here. So that diagram what is showing, like one is, you can see the Pelton turbine, another one is the reaction turbine. In the reaction turbine, two things I have taken, as I told you, that one is for Kaplan, another one is for Francis one. So in the first one, we'll try to understand what is going to define or what is going to say. So we have taken 6 parameters. First, keep in mind that we have taken 6 parameters: speed, head, discharge, power, and efficiency, and gate opening. So what we are going to discuss here today, main characteristics curves, which is nothing but at constant head curves also. So the diagram is what is showing here. This is for Pelton turbine. So the Pelton turbine, here H is constant, here head is constant. So if you remember the Pelton turbine, okay, this is the wheel part is there, or you can say this is the runner part is there. So in the runner, we have number of buckets are there. So number of buckets are installed or mounted on the wheel, we can say. Okay. So this is the number of buckets which are mounted on the wheel. And in this runner is like, attached with the, you can say the shaft. So in this, the jet is striking here. Just I'm giving a recap of this. So the water of this jet is coming out from this pipe or from the nozzle, we can say, and that is going to strike to this bucket. So here what, like unit speed. So unit speed of what? The unit speed of this runner, we can say. The runner is nothing but the total part. This is the runner part or wheel part is there. So where the number of vanes are mounted. So unit speed and unit discharge. So discharge means what? The quantity of water or the volume of water which is coming out from the turbine, we can say. Now this unit speed and unit discharge, somewhere you can see only N versus Q also we can see. So these terms like NU versus QU and NU versus Q, both you can consider the constant, like same things are there. Why I'm talking about the same? Because we have seen that previous lectures that our unit discharge equal to, unit discharge is nothing but the discharge with respect to root over of H. That means here head is constant, means here H is constant I have taken. So if H is constant, then we can write QU equal to Q. Okay. Similarly, I can say if I consider the unit speed equal to, we know that N by root over of H. These two things we have seen in our last lectures where we are calculating the unit speed, unit discharge and unit power. So here also, if I consider the H is constant, like then I can say that unit speed equal to nothing but speed. Okay, so nothing wrong on this. We can consider this one because we have considered that head is constant. So at a head constant, the height of this turbine working is constant. We need to compare unit speed. So unit speed of what? The unit speed of the turbine. We need to consider at turbine rotation or turbine speed. What about the discharge? So here what we are seeing here, that this one you can see, this is gate opening actually. I told you one more point, that is gate opening. This is also one parameter. So the gate opening, that means when you open, like the gate opening in the sense, the water which is coming here like through the penstock, here we have a spear or hand wheel is to there, which used to work like a valve type. If you open the gate, so this one if you consider as a gate, if I open the gate 1/4, okay, if you consider the 100%, out of 100%, if I open this one 25%, suppose if I open the 25% of this gate, then what about the speed? Like speed, once you open this one, what is the discharge from this turbine will come out from here. So here what will be there actually, your QU or that unit discharge, or you can say the Q will be constant. This will be, Q will be constant with respect to the unit speed, because see the speed then the speed may increase, okay, but discharge which happening by how it is working we need to understand. So the water is coming out from the pipe and is going to strike here. So after striking, this is continuously running, but the water will be fall here. Okay, so there will be no loss in this, and we know that also like Q equal to AV. So discharge equal to area into velocity. Now one more thing, V equal to, we know that root over of 2gh. Now head is constant, so this part is constant. So here velocity will be constant here. Now discharge part will be constant, remains constant along with the speed. Because see, runner may rotate with high speed or low speed or medium speed. Okay, that does not affect any kind of effect on the discharge part. So because nozzle here, if you see the nozzle here, okay, the nozzle is operating with a fixed running point here. So when it is impacting or when it is affecting this bucket, okay, it started rotating, but the discharge from this is nothing but it is coming to the tail race. Okay, so there will be no loss of water by carrying this one, and there will be no effect of this discharge with respect to speed. So here, as I told you, this part actually runner. This is our runner, this is our shaft, and this is our nozzle part is there. Okay, so the runner speed or runner, this is the runner speed. Okay, so this runner speed actually do not influence with the jet flow. Okay, do not influence with the jet flow, and so the change of unit speed do not affect the discharge. Okay, so that's a very simple thing is there, like the change of unit speed. Unit speed, which one? As I told you, this is the unit speed is there, or the change of speed, we can say. The change of speed do not affect the unit discharge or discharge. So here discharge will be constant here. As I told you, discharge will be constant. So here what will get? A Q equal to constant at increment of unit speed. Then one more thing I told you, that 25% of gate opening. Okay, so the gate opening also, like it may be 25%, this is suppose 50%, and this is 75%, and this is full gate opening in the sense 100%. So how much gate will be open, that much discharge will be there. So same thing, like 50% open, 75% open, then 100% open. So there will be no effect on that. So this is for the Pelton turbine or Pelton wheel. But coming to this Francis turbine and the Kaplan turbine, it is not like that. It is different, because if you remember the construction of the Pelton turbine or Francis turbine, like Kaplan turbine or Francis turbine. So in that, actually this is coming under the reaction turbine, and this is, as I told you, this is coming under impulse turbine. This is impulse and this is reaction. We have one Kaplan, another one is Francis. In the Francis turbine, actually, if you see, as with respect to the unit speed, the unit discharge is decreasing. Like how much speed is, with respect to speed increasing, our discharge is decreasing here. I'll tell you what is the reason for this. And these are the gate openings are there. So gate openings, see, gate openings will be fixed. There is no change in the gate openings. Like if you see, this is our only. At this point, your gate opening is fixed. At this point, gate opening is fixed. At this point, gate opening is fixed. That means 25%, 50%, 75%, 100%. Or that is nothing but 1/4, 1/2, 3/4, or full gate opening. Similarly, here also same thing. So here also 25% of gate open we can say, and here also like 50%, as I mentioned previously. This is 75% and this is 100%. So in the Francis turbine, if you see, with the increase of the speed, okay, now okay, let me tell you like how it is. If you remember, like this is our runner part is to there, and this is our entrance of, you can say, the water from the penstock, and it used to like this. So the water used to come from the penstock, and it used to travel through this casing. This is our casing used to there, and here we have the runners are there, or blades are there, which are fixed here, you can say, and this is the shaft is there. And before to this also we have some guide vanes are fixed in this. So that means two types of vanes, one is guide vanes, another one is runner vanes are there. So the water which is coming out from outside, that used to goes to this turbine through this guide vanes. Okay, that we have discussed previously. So why I am reminding these things, because here when it is rotating, when this runner is rotating, this is to create a centrifugal force because the water is coming here radially. Keep in mind, for the Francis turbine, the water is to flows in radially. In the Francis also, again, two types are there, like old Francis turbine, another one is new Francis turbine, modern Francis turbine. In the older Francis turbine, it used to consider, like it used to act radially, like in that also again inward radial flow and outer radial flow is there. But in the old Francis turbine, mostly the water used to flows radially and is to go out also radially. But in the modern Francis turbine, it is to consider that the water is to come radially inside and it is to leaves axial. That's why it is called mixed reaction turbine. Anyway, so this is the Francis turbine. In this, actually, the centrifugal force is developed. Okay, the centrifugal force is developed in this, and here the centrifugal force, when it will be developed, now when the water is striking to this one and it started rotating, there the centrifugal force is to work act on this. So in this case, actually, the runner is to, for the first case, you can say the runner is to rotates very faster. The runner is to rotates very faster, and with the runners, the centrifugal force also acting, the centrifugal force on the water, that also increases. Centrifugal force also increases in this point, and the pressure difference, we know that here we have the pressure difference used to occur here at the blade. One side one pressure will be there, and other side of the when after striking to that, when it is going out, there will be a less pressure. That means there is a pressure difference. So the pressure difference which is created here, that is to reduce the runner. Okay, that is to reduce the runner. And the centrifugal force, this centrifugal force, actually that is to oppose the inward radial flows of water. Okay, this is because we know that, as I told you, that in your inward radial flow, one is having inward radial flow and another one is outward. Inward means from outside to it's going inside. So when the centrifugal force developed here, so this centrifugal force actually that is to oppose the inward radial flow. You can say the inward radial flow of water. The inward radial flow of water. Okay. So when it is like when there is a restriction, you can say there is a restriction of water to goes inside to the turbine. That means the entry of the water into the runner is difficult. So once entry of water is difficult to the turbine, so obviously the discharge will be also reduced. And also we can explain in such a way that when it is a centrifugal force developed, the water is to discharge outside. Okay, and like on behalf of going to inside, that through the runner is supposed to exist, it is to discharge outsides. Okay, and that's why I told you that centrifugal force oppose the inward radial flow, because we, as I told you, that inward radial in the sense from outside the water is to goes inside through the veins, guide veins. Then after that runner will be there. In the runner again veins will be there. So the water which is coming out, but when it is when the centrifugal force created here, that acts as a, when it is rotating, you can say, okay, the water is to goes outside here, outside. Okay, so by that the flow reduced. Once the flow reduced, obviously the discharge also will be reduced. So this is the point in the Francis turbine. You can see here Francis turbine, unit speed is there, so unit speed increasing. But what about the discharge? As I told you, the discharge, see, these are the lines are there, these are the lines for actually, as I told you, gate valve openings. Okay, so here if you suppose we have a valve is there, and the valve if you operate, okay, with 25% opening and 50% opening, then 75% opening, then full opening, based on that it will be acted. Now, while coming to this Kaplan turbine here, this is Kaplan turbine, same head is constant, and at this condition, but we'll get some reverse to this one, because here actually in the Kaplan turbine we have this is x-axis unit speed and y-axis our unit discharge. Here also the same thing, 0.25 like 1 by 4, and this is 1 by 2, 3 by 4, and this is 1. So that means 25%, 50%, 75%, and full gate opening. So in the Kaplan turbine, if you remember, actually there like shaft used to connected, and here we have a runner that is called actually hub or boss, if you remember, and along in this also our vents are attached in this, and the water used to come out from this side, okay, and that is to strike to these veins, and it is to come out from this turbine axially to outside. So this is, as I told you, this is our radial flow. Okay, this is our radial flow, and this is our tangential flow, and this is our axial flow. This is nothing but axial flow. So here what will happen, the flow is parallel to the shaft. If you see, this is our shaft actually, what I have drawn. This is our shaft. So the flow which is coming out from here, after striking, it started rotating. Once it started rotating, the flow is coming out from here. So for this condition, the flow, you can say, is parallel. The flow is parallel to shaft, and this is called axial flow turbine. This is called axial flow turbine. So here what will happen, the centrifugal force do not oppose the flow directions. Okay, here after striking, you can see, after striking the water on this blade, okay, it used to happen directions here, but again we have that at the end of this turbine we used to have a draft tube. Anyway, the water will be in the draft tube itself, it won't go out. Okay, so there will be no difficulty when the water is coming out from, like when the water is striking on the vents which is connected to the runner, and here the centrifugal force, we can say, it won't affect that much because it won't oppose the flow, we can say. Now once increase the speed, now see, once you increase the speed of the runner, okay, and that improves the suctions also. Okay, and see, when increase the speed of the runner, as I told you, when the increase the speed of the runner, then that will be create a suction at the outlet condition. So at the suction at the outlet condition means the discharge will be more at that point. Okay, so these blades will be allowed more amount of flows from the out. So that's why here if you see that speed increases, the speed increases, our discharge also increases. With respect to the gate openings also, it will be like same. So this is for one gate opening, this is for one gate opening, this is for one gate opening. Different gate openings, we have different graphs are there. So this is about of constant head with respect to unit speed, unit discharge for two different turbines. Now we'll see the next one. The next one is quite similar. So first one is that at head constant, see, head is constant for this characteristic curves, and with respect to the head constant, we'll see this is the diagram for, see, unit speed with respect to unit power. Here also unit speed with respect to unit power. So this diagram I have taken, you can say here, this is Pelton turbine. This one I have taken for the Pelton turbine, or which is called like impulse turbine also, and this one I have taken for the reaction turbine. So in the reaction turbine, as I told you, the two types are there. One is Kaplan and another is Francis. So in the Pelton turbine, now the diagram started here. See, here also same thing. 1 by 4 gate opening, 1 by 2 gate opening, 3 by 4 gate opening, and full gate opening. So 1 by 4 is nothing but 25%, 50%, 75%, and this is 100%. Okay. So now we can see this unit speed versus this is unit power. So this is nothing but we can say that as unit speed increases, initially the power started increasing up to a certain limit. It is there. Then after that it started decreasing. Okay, initially at the increasing mode, but at the initial also you can see very low power developed or no low power raised, you can say. So for that, what I can say in this, as the speed increases, okay, as we have seen that Pelton turbine is a impulse turbine, or it is coming out of the tangential flow turbine. So here the pressure will be produced, okay, due to a change of momentum, because no, here the power actually, okay, not the power. So one thing, just keep in mind, the power is nothing but the power how is to produce, okay. So power will be produced by changing of momentum, if you see this diagram, see, when the jet is striking on this bucket, okay, the momentum of this runner changed, okay. So how much fast it strikes, that much fast it will started running here. So the power will be changed, or it will be produced due to the power will be produced, we can say, by changing of momentum. So how to change this momentum here? So at the low speed, if you see low speed, that means at the low speed we can say the runner obviously it will be moves slowly. So low speed, our runner moves also slowly, okay. So in that point the jet strikes the bucket, but the energy transfer will be not possible, and very less energy will be transferred in that, so that we can say the energy transferred but very less, energy transferred but very less energy was transferred there. So at the low speed our low power developed. Even in low energy transferred means, that means low energy, no low momentum created, and low power will be developed here. So once it started increasing, as the unit speed increases, like at the speed increased, you can see at the speed increased, okay. So the bucket also again, if you see that diagram, when it's striking here with a high speed, like speed increased, then this bucket also struck very fast, and it started moving, rotating very fast, okay. So here at the speed increase, the bucket speed also or the vane, or you can say the bucket, which also will be start very fast. And here the momentum will be also, the momentum which is directly related to this one also will be very fast. So the momentum change very fast, in the sense the power also will be developed very fast, or we can say the power also increased very fast due to this one. This one, just to remember this point so that we can easily understand. But after reaching a particular speed, a unit speed, okay, we have derived one equation previously, if you remember. There I told you that bucket speed will be equal to half of the jet speed, okay. This one we have already derived previously. So after a certain point, okay, how much bucket speed may be, okay, so that will be like half of this jet speed. So the energy transfer will be maximum at that point, at this point, and here we'll get the maximum efficiency also. Even in the efficiency term also, if it will come, I'll show you the similar kind of diagram for this also, okay. So in this point, that high, if you go very higher also, at the higher speed of this turbine, okay, the bucket will be move very fast. As I told you, bucket will be move very fast, but the jet cannot able to, okay, stroke the bucket properly or strike the bucket properly. As I told you that buckets, like, you know, the bucket is moving very fast with respect to the as it is attached to the runner, but bucket cannot be properly struck by the jet, though due to the very high speed is there, very high speed of jet is there. You can say, or you can say the very high speed of runner is there actually. So the jet cannot strike properly to the bucket, okay, because the jets started slipping, okay, over the bucket, because very high speed is coming, few what will be losses will be there in that also, again losses will be there with the high speed, and the bucket cannot able to change its momentum properly. So once momentum cannot be changed properly, we cannot reduce more power in that. So power started reducing in that perspective of view. Okay. So here the concept is like of this gate opening is nothing but if you increase the gate opening, simple thing, increase. Initially gate opening is 25%, next is 50, 75, 100%. Increase the gate opening, we can get more discharges there. Okay, that we have seen. And more discharge means increased gate opening, discharge is more. Now here, when discharge is more, obviously we can get more jet momentum is there. We can get more jet momentum. And more jet momentum in the sense, obviously more power is there. So same thing here also. If you see, this is for 25%, 50%, 75%, 100%. So each go to gate opening, we have maximum power generated for this. Okay. And as I told you, the power for less speed, how this power was generated, and medium speed or at optimum speed, how this power is generated, and at the high speed, how this power is started reducing due to is not properly matched. Okay. This is for the, you can say, for this Pelton turbine. Similarly, for the reaction turbine, also same thing, similar things is going to also identify from here in the reaction turbine. So in the reaction turbines, just I will give a similar kind of concept, but it's slightly different. I will start from the, see this power and efficiency. See here also I can tell the same thing, like this power and efficiency is both are connected, because we know that efficiency equal to output by input. So output is nothing but here output power by input power. Output power by input, or output by input you can say. So here output means in the sense what? Now what is the power developed? What is the power developed finally? And what is the input power? Input power is nothing but here we used to consider the water power. And the power actually produced here how much with respect to this one actually rho g QH by 1000 we used to write. Okay. Now if I write this power terminology here, so what I can write, power equal to, this is, you can write rho g QH, and this efficiency if I consider into this 1000 will be multiplied here suppose. Okay, let's consider only this term, this 1000 term, no need to consider right now, or you can multiply in this also in terms of kilowatt. If you consider, then you can consider. Now if you see, this power is equal to rho g QH, H and H into efficiency term. Now this power if I take directly proportional, then what will come? Q will come here and efficiency will come here. Q and efficiency, because density constant, G constant, and head we are consider as constant head. So because head is constant we are discussing, correct? So let consider head is constant. So power is directly proportional to Q and efficiency. So here power, what you will get, similar kind of diagram will get for the efficiency also. So this is also for the Pelton turbine. This is for Pelton turbine, and this is for reaction turbine. Okay, this is for reaction turbine. So here, as we can see that for the reaction turbine power we are discussing, correct? So at the low speed, we can see the runner started rotate slowly. Okay, the runner started moving slowly because low speed is there. So obviously the runner will started moving slowly. So here we'll get velocity triangles. We have the velocity triangles of, okay, the jet, velocity triangle of the jet at the inlet case. So the velocity triangles are properly not formed, or you can say it's not optimal. And due to these velocity triangles are not optimal, so here the flow separations will be started. The flow separation will be started in the initial conditions. At the low speed, the flow separations are more. And though these flow separations are more, so you will get efficiency, low efficiency will be there. And due to low efficiency, your power also low. Or you can say low power is there, low efficiency will be identified. Similarly, at the intermediate speed, you can see that intermediate speed, it will be like, maximum will get like this. So maximum power is achieved at this point, or you can say at this point also. Slightly right it will be there. Okay. So at the intermediate speed, if you see, okay, the velocity triangle, well, it started little bit improving. Okay. If you remember the velocity triangle, what we have discussed previously, the velocity triangle started improve, and the water enters to the runner very smoothly. Previously, it is difficult to enter. Not that much because less speed is there. That's why it is less. And once the velocity triangle started improving, so water started enters to the runner very smoothly. So there, then the conversion of power and velocity energy, that's not power, you can say the pressure and velocity energy. Pressure energy and velocity energy is there. Pressure energy, velocity energy in the sense kinetic energy. Okay, so the conversion of pressure energy and kinetic energy, okay, that will be converted very effectively in the intermediate speed. So at this point, you can get the maximum efficiency can be identified from here, so that our power also will be maximum at this point. Okay, at the high speed, what will happen? That means here for the reaction turbine specifically, in the reaction turbine, your centrifugal force is there. So the centrifugal force is more significant at the high speed. Okay, so the centrifugal is more significant at the high speed. So the flow separation will be started here. So flow separations increased at this point at the high speed. This is for high speed. Okay, similarly losses also will be more here. Here losses will be also increased. So if losses increased, your efficiency started decreasing. Efficiency decreased, power also decreased. And the role of gate opening also, you can see that high gate opening, more discharge. I already told you that high increases of gate opening, that means gate opening increase and discharge increase. Discharge increase, more momentum or more power is generating here. This is the role of gate opening. Similarly, in the efficiency case also, as I told you that both are directly proportional to each other in the power and efficiency term. So this is that efficiency, overall efficiency with respect to unit speed for the Pelton turbine. So this is for the 25%, 50% gate opening, then you can see 75% gate opening, and this is 100% gate opening. So the similar kind of plot can be identified from here for this Pelton turbine when H is constant. And similarly, at H is constant in the reaction turbine also, like similar to this, also we'll find out the at low speed will have the low power or low efficiency generated. At the optimum, you can see at optimum, like at optimum speed, we'll get the maximum efficiency, and after that it started also decreasing. The efficiency also started decreasing, even the speed increased here. So this is all about the constant head. This is constant head curve, or it is coming under main characteristics curves. So I hope you understand this theory. It is slightly lengthy, but very interesting to understand. If you are having any kind of doubt regarding this or any query regarding this, you can give a comment on the comment box. Thank you all.